In this video, we're going to be talking about the tangent line of a circle. And when we say the tangent line, tangent means touch. So we're talking about the line that just touches the circle at one single point. So the tangent line to a circle would look something like this. If we draw in the radius of a circle, let's say we're going to draw in the radius over here. So we have the radius of the circle, and we can see that the radius touches the perimeter of the circle at this point right here. So the tangent line to the circle at this particular point would be the line that passes through this point and no other points on the circle. So maybe that would look something like this, but basically it would just be the line that touches the circle only at this exact point right here. Now obviously we could have a tangent line at any point around the perimeter of the circle, but this is the specific tangent line at this point. And the way that you know that a line is tangent is if you have a right angle between the radius and the tangent line. So if you're ever shown a diagram like this and you have the radius and you have a line that intersects the radius right here and then this 90-degree angle to indicate that this line and the radius are perpendicular, then you know that this line is tangent to the circle. The way we can prove that is with the Pythagorean theorem, because if you think about it, if we, for example, talked about this point on the tangent line right here, and we connected this point to the center of the circle with a line, what we'd have, of course, is a right triangle with this 90-degree angle right here. And what we can say is that because the 90-degree angle is right here, this green line, of course, is the hypotenuse. And the hypotenuse is always going to be longer than either of the legs of the triangle. More specifically, this hypotenuse is always going to be longer than this leg, which is the radius. So if we pick any point on the tangent line other than the point of tangency, we know that this hypotenuse is going to be longer than the radius, which means that this point is going to always lie outside of the circle. And it doesn't matter which point we pick. If we come in a little bit closer here and we pick this point, right, and then we connect it with a line to the center of the circle, we can still see that this is the hypotenuse, that this point is going to lie outside of the circle. And so what you can see then is if we keep picking points that are closer and closer to this point of tangency, it doesn't matter how close we get, those points are always going to be outside the circle because the line between those points and the center of the circle represents the hypotenuse of a right triangle, which is going to be longer than this radius, which means that the only point on the circle is in fact the point of tangency, which proves that the tangent line only touches the circle at this exact point. So the point is that as long as you have a 90-degree angle between this line here and the radius, you know that this line is the tangent line to the circle. So how do we apply that to a more specific problem here? We've been asked, what's the signal range of a cell tower if we have a cell tower standing on the Earth that's 1,500 feet tall? We know that the diameter of the Earth is approximately 8,000 miles. And so we have this diagram here of the Earth. We have the cell tower. We know it's 1,500 feet tall. And what we can imagine is that its signal range goes, in both directions this way, and it can only reach from this point here to this point here on the Earth. Outside of this range, this signal tower will have no effect. So what we're interested in is the range, and we'll go ahead and call the range here D, and that'll be the distance between this point as far as it can reach and the top of the cell tower. We've also been told here that this is a 90-degree angle. So since this is a 90-degree angle, what we know is that we have this right triangle, and we can think about the point of tangency that goes through this line here to the top of the cell tower. We can also say then that we have the hypotenuse of a right triangle from the center of the circle to the top of the cell tower here. So if D is the range of the cell tower, and that's our unknown distance, that's what we want to find, we need to know the lengths of the other two sides, and then we can use the Pythagorean theorem to find D. So what about the length of this side? This is one leg of the right triangle. Well, we've been told that the diameter of the Earth is about 8,000 miles, which means the radius of the Earth is half that, about 4,000 miles. So we can go ahead and say that this is going to be 4,000 miles. That's the radius of the Earth. What about the hypotenuse then? Well, if we think about here the distance between the center and the edge of the Earth, right, we know that that is also 4,000 miles because that's just the radius. So then we just need to add to 4,000 miles 1,500 feet. But we can't really add miles and feet, so we're going to need to convert 1,500 feet to miles. The way that we're going to do that is by recognizing that there are about 5,280 feet in 1 mile. So to get 1,500 feet in terms of miles, all we do is we take 1,500 and we divide it by 5,280. And when we do that, what we get is a decimal about 0.2841 if we round it to 4 decimal places. So this is approximately equal to 1,500 feet. We can call this 0.02841 miles. So then the total hypotenuse here, which we can call C, is going to be equal to 4,000 miles plus 0.2841 miles, or 4,000.2841 miles approximately will be the distance between the center of the Earth and the top of the cell tower. So what that means then is that if we think about this in terms of the Pythagorean theorem, we have a value for one of the legs, which we'll call A. So if we plug 4,000 in for A, we're going to get 4,000 squared. B is going to be equal to our unknown distance D, the range of the cell tower, so we'll go ahead and say plus D squared. And then C squared is going to be the length of the hypotenuse squared. We already know that the length of the hypotenuse is 4,000.2841 miles, so we're going to say is equal to 4,000.2841 squared. And then if we do the math here, what we're going to see is that 4,000 squared gives us 16 million, that 4,000 and a decimal squared is going to give us 16 million and change. And then if we take the 16 million and change and we subtract the 16 million, and then we take the square root of that value, since we would have D squared is equal to the difference of this minus this, we take the square root and we're going to get D is equal to approximately 47.67 miles. And so then what that tells us is that the signal range of the tower is about 47 2/3 miles in each direction. So we can say D is equal to 47.67. So this cell tower here can reach about 47 miles in this direction, and it can reach about 47 miles in this direction before you're out of range of the cell tower. So then as a practical application, if you think about the company that builds these cell towers, they're going to want to build another one, let's say right here, that can also, if it's the same height, can also reach 47 miles in this direction and 47 miles in this direction, so that no matter where you are, if there's a person standing here on the Earth, they're going to be reached by one of the cell towers. If they go a little bit toward this cell tower, they'll be covered. If they go a little bit toward this next cell tower, they'll be covered. But either way, this would tell the cell phone company how far apart to space their cell phone towers. And that's how you use the tangent line of a circle to solve a problem like this one.